This is the first actual lecture of CHM 225, and you'll find the notes for this all posted on Blackboard separate from the course notes. And we have to kind of leap ahead and talk about redox chemistry in preparation for our first experiment, where we will be carrying out electrolysis of water. So this is a bit out of place, but you need to know this, so it's as good a time as any. So oxidation reduction reactions, often called redox reactions for short, they involve the transfer of electrons. Notice the picture over here. We can say that cars rust. They rust, they do. Why do they rust? Well, they're made of steel. Here's a photograph of a steel bolt that's clean. The surface is cleaned and it displays the characteristic dull gray color of steel, which is mostly iron. On the right hand side we have again a steel bolt, but this time it's been rusted. And the term for that is oxidized. It reacts with oxygen, so it's oxidized. And the orange-brown coating is iron 3 oxide or rust. What's happening chemically when oxidation is occurring here? So the element iron is reacting with oxygen to produce iron 3 oxide. Let's start by writing the oxidation numbers of the atoms and ions in this compound. What's the oxidation number of iron? It's 0. All the elements have an oxidation number of 0. That means they have no charge. They have the same number of electrons and protons, so the neutral oxidation number is 0. The same is true for the diatomic elements, like oxygen. Its oxidation number is 0. So all elements on the periodic table have an oxidation number of 0. When they gain or lose electrons, then they have other oxidation states. What about Fe2O3? Let's figure it out. So we know that oxygen is almost always -2, with few exceptions. And I see from the formula that there are 3 oxygens, so 3 times -2 is -6. The total negative charge for the 3 oxygens is -6. Now the total charge on Fe2O3 is 0, unless otherwise shown. The total charge is 0. And therefore the total positive charge for the 2 irons must be +6. And dividing that +6 by the number of ions present, each one therefore is +3. So the oxidation number of oxygen in Fe2O3 is -2. The oxidation number of iron is +3. So when iron was oxidized from oxidation state 0 to +3, did it gain or lose negative charges? To go from 0 to +3, did it gain or lose negative charges? It had to lose negative charges to become more positive. In fact, it lost 3 negative charges, which are electrons. Right? And losing electrons has a name, and that's called oxidation. We define oxidation as the loss of electrons. So when iron is oxidized, it's actually losing electrons. Now oxygen, in the same process, when it goes from 0 to -2, is it gaining or losing negative charges? Well, each oxygen atom is going to gain 2 negative charges or electrons. And the name for that is called reduction. Reduction is the gain of electrons. Now I've deliberately not balanced the equation because I want to focus on individual atoms, because I want to just explain the concept here. So some terminology you need to learn. Oxidation and reduction. So if you remember this mnemonic, Leo the lion says, what would he say? I don't know. He says grr. So loss of electrons is oxidation. A gain of electrons is reduction. Now, when this occurs, oxygen, which is doing the oxidizing, is called the oxidizing agent. Whatever does the oxidizing is called the oxidizing agent, or sometimes it's called the oxidizer. So the oxidizer is going to gain electrons or take electrons to oxidize something. The iron, on the other hand, which is being oxidized, is called a reducing agent. It's going to reduce the oxidizer. By reducing, it means you're going to give it electrons. In every redox reaction, you have to have oxidation occurring at the same time as reduction, so you will always have an oxidizing agent and a reducing agent. Just like in an acid-base reaction, you have an acid and a base. Both have to be present in order for the reaction to occur. Oxidation numbers, where do they come from? Well, it depends on the type of compound. In ionic compounds, and I'm going to use lithium fluoride as an example, the oxidation number is simply the electric charge on the ion. Let me draw this. We'll draw a Lewis structure for the reaction. We'll say lithium, which is in group 1A, which means it has one valence electron. All elements in group 1A have one valence electron. It has an electron configuration identified by S1, and we'll talk about this later. You probably already know it, but in case you don't, we'll cover it later. There's a single valence electron in lithium. It reacts with fluorine, and fluorine is in group 7A, which means it has 7 valence electrons. They're identified by S2P5. Here are its 7 electrons in the valence shell. Now when they react, what kind of bond do they form? You look up the electronegativities of the atoms in Linus Pauling's table of electronegativities, and I've given them to you here. Fluorine is the most electronegative element on the table. Its value is 4.0. Lithium is quite low. It's actually electropositive, we would say. Its electronegativity is only 1.0. The difference is 3.0. Then we look on this table that compares difference in electronegativity to bond type. So this is delta En is difference in electronegativity. You always take the more electronegative atom first and subtract the lesser value because we want positive differences. Read the top scale if it's a metal to nonmetal bond, as in this case, metal to nonmetal. Read the bottom scale if it's nonmetal to nonmetal or nonmetal metalloid. So in our case, the difference is 3.0. It's way up here. It's clearly ionic bond. What that means is that ions are formed. And to show that, we draw arrows to show the movement of electrons. So lithium is going to donate or have its electrons taken, depending how you visualize that, by the fluorine. Now in chemistry, we draw a single arrowhead, like so. Sometimes it's called a fishhook. That refers to a 1 electron transfer. If we're having a 2 electron transfer, we would draw it with a fuller arrowhead. Now this is not a big deal at this time, but later in organic chemistry we make the distinction, so I might as well show you correctly to begin with. Okay, so what's that going to form? Well, the product will be a lithium cation. It lost its valence electron, therefore it's plus, and fluorine gained an electron, so now it is actually an anion named fluoride. Negative charge. Now I just put the square brackets in to reinforce that those electrons belong to the fluorine, they're not being shared. This is an ionic compound, and the oxidation number of ions in an ionic compound is the electric charge of the ion. So the oxidation number of lithium is +1 in this compound, and the oxidation number of fluorine is -1 in this compound. So it's that simple. But you say, well, what happens in covalent compounds? Covalent compounds are not made of ions. Well, let's take water as an example. The oxidation number is the electric charge that each atom would have if the atom were made of ions. Let's draw the Lewis structure of water, and I'll explain what I mean by that. Hydrogen is group 1A, S1 electron configuration, 1 valence electron, reacting with oxygen in group 6A, S2P4 electron configuration, 1, 2, 3, 4, 5, 6 valence electrons, and then we have another hydrogen for H2O. Right? So when they form a bond, we calculate the difference in electron negativity between oxygen and hydrogen. 3.5 minus 2.1 is 1.4. What type of bond is that? We have to use the lower scale because it's a non-metal bond, and 1.4 falls in this range, polar covalent, which means electrons are not shared equally, but they are shared, they're not transferred. To show the sharing of electrons, I'm going to say one electron from here comes over and joins that one from here to here. Oxygen would like to have 8 electrons in the valence shell to be like the nearest noble gas, neon. Hydrogen would like to have 2 electrons in the valence shell to be like its nearest noble gas, helium, but neither can take electrons from the other, so we draw a covalent bond like this. We show the Lewis structure of water as being HOH. Now these lines represent electron pairs that are shared. They're not necessarily shared equally, but they're certainly not ionic. Which reminds me, you must never write a structure like this, as I do see from time to time, for an ionic compound. This is not correct, because that implies electrons are being shared, and they're not. So in the case of water, what's the oxidation number of hydrogen? What's the oxidation number of oxygen? Well, remember that oxygen is the second most electronegative element. It really would like to take electrons, and hydrogen is not nearly as electronegative, so the electrons spend most of their time near the more electronegative atom. They spend more time here. And so let's go back to what was underlined here. The oxidation number is the electric charge each atom would have if they were ions. So if H2O was actually made of ions, what would it be? Well, it would look like this. H plus, O minus 2, and H plus. So if water was ionic, it would look like this, in which case the oxidation number is +1 for hydrogen and -2 for oxygen. And it works, because those are correct. So that's the concept. But that would be really tedious to have to do that every time we want to figure out the oxidation number on an atom, and we need them all the time in chemistry. We really need to know that. There's an easier way to do that. If you look at a periodic table, there are a variety of oxidation numbers for many elements, but some of the elements have what are called fixed oxidation numbers. They only occur in one oxidation state, and there's not that many of them, and they're easy to know where they are. And once you know that, you can figure out all the rest quite readily. So let me walk you through that. We'll start on the left-hand side. The alkali metals, lithium, sodium, potassium, rubidium, cesium, francium, in group 1A, all of their chemistry is about losing that one electron and forming a +1 cation. In all of their compounds, there is no exception. All of the alkali metals, lithium, sodium, potassium, rubidium, cesium, francium, they're always +1, and they're in group 1A. It's easy to remember. Furthermore, silver is always +1, and notice silver is in group 1B. What a coincidence. I say, what about hydrogen? Well, hydrogen is often +1, but not exclusively. Hydrogen, remember, is not a metal. It's a non-metal, so there are occasions where it will gain an electron to become like helium. In such cases, it's -1. So hydrogen is either +1 or -1. Those are the only two options for hydrogen. You might say, well, when would hydrogen become an anion? Well, for example, if hydrogen was going to react with sodium, sodium is less electronegative than hydrogen by a significant margin, and so the sodium would give up its electron and hydrogen actually take it, and you'll get what's called a hydride anion. But that only occurs with the alkali metals and some of the more reactive alkaline earth metals. More about that later. Okay, so those are the +1 oxidation number elements. Now it gets even easier from here. The group 2A elements, beryllium, magnesium, calcium, strontium, barium, radium, the only chemistry they ever exhibit is that they lose 2 electrons, and therefore in all of their compounds, no exceptions, the oxidation numbers are always +2. And zinc and cadmium are always +2, and guess what? They're in group 2B. So that's pretty easy to remember. Move to group 3A. Group 3A elements would like to lose 3 electrons. Turns out that boron, aluminum, and gallium are always +3 in all of their compounds, and they're in group 3A. You say, what about indium and thallium? Well, +3 is a common oxidation number for indium and thallium, but it's not the only one, and I want to register or focus on those that have fixed oxidation numbers. Group 4A elements that have +4, always silicon and germanium. So what about carbon? Well, carbon is like super element. Carbon forms pretty much an infinite number of compounds, and it can have all kinds of oxidation numbers, 2.6, 4.3, you name it, could be anything. That's a whole series of courses in itself on carbon chemistry. Now let's move over to the right-hand side and talk about the halogens next. Fluorine is the most electronegative element on the table. Nothing can take an electron from fluorine. In fact, fluorine is always taking electrons from anything else, so fluorine is always -1 in all of its compounds. Let's look down the halogens. What about those? Chlorine, bromine, iodine. Take a look at a periodic table here. Notice the values for chlorine. +1, +3, +5, +7, and -1. Bromine, +1, +5, and -1. Iodine, +1, +5, +7, -1. So obviously, when chlorine or bromine or iodine are the less electronegative element, they could have multiple different oxidation states. But when chlorine or bromine or iodine is the most electronegative element in a compound, it can only be -1, because that's the only negative oxidation state that the halogens ever have. Why is that? Well, they're in group 7A. If they could gain 1 more electron, they become isoelectronic with the nearest noble gas. Gaining 2 or 3 would never be right. It would be reactive. It would only gain 1. So, when the halogens are the most electronegative element in the compound, they're always -1. 7 plus 1 electron makes 8. That's pretty easy, right? Let's go to group 6A. Oxygen is the second most electronegative element in the periodic table. Electronegativity is 3.5. There are very few compounds, well really only fluorine, that can take electrons from oxygen. So in almost all of its compounds, oxygen would like to gain 2 more electrons to become like neon. And so it's almost always -2. You're probably aware of an exception where in peroxides it's -1. And unless the name of the compound contains the word peroxide, you can be sure the oxygen is always -2. Take a look at sulfur, selenium, tellurium on the periodic table. Group 6A. Notice sulfur can be +2, +4, +6, or -2. Selenium +4, +6, or -2. Tellurium +4, +6, or -2. So what's this telling us? When sulfur, selenium, or tellurium is the more electronegative atom in a compound, it will always be -2. Why -2? Because it needs to gain 2 electrons to become like the nearest noble gas. So it's going to be -2. -3, -4 just wouldn't work. Neither would -1. Okay, how about group 5A? Let's take a look at the periodic table. What do we see? Nitrogen can be 2, 3, 4, 5, or -3. Phosphorus 3, 4, 5, or -3. Arsenic 3, 5, or -3. Antimony 3, 5, or -3. So what's going on here? Well, you can see that when these group 5A elements, the nitrogens, are the less electronegative element, they could have multiple oxidation states. But when they are the more electronegative element in the compound, they can only be -3. Why -3? Because gaining 3 electrons make them isoelectronic with the nearest noble gas, and that gives stability. Gaining 2 or 1 or 4 just doesn't cut it. So -3, -3, -3. Looks like I missed a couple here. Selenium -2, tellurium -2. So those are the elements that have fixed oxidation numbers or under special conditions we can relegate them. If you can learn those based on their position in the periodic table, you can then calculate any other oxidation number in a compound. For example, here's potassium permanganate. What's the oxidation state of manganese? Manganese has 5 different oxidation states it can exist in. But look, it's attached to potassium, and potassium is always +1. It's an alkali metal. Oxygen is virtually always -2, and there's 4 of those. The total negative charge is -8. Potassium is +1. The total charge on this compound, unless otherwise shown, is 0. As a chemist or chemical technologist, you have to learn to see the invisible zeros. Only us chemists see them. Other people are jealous. There's an invisible 0 over everything that doesn't have a charge. The total charge is 0, therefore manganese must be +7. +1 +7 +-8 equals 0. So we can calculate the oxidation number of any atom and a compound if we memorize these that have fixed oxidation numbers. So I commit them to you to memorize it. You must do so. We need to look at the electrolysis of water because that is part of the first experiment. The first lab is about hydrogen, and so electrolysis is an important part of that. And electrolysis is so important in chemistry and technology that you need to learn it at any case. Let's start now. Make sure that you watch a link, a short video clip. It's entitled Eudiometer. A eudiometer is a device in which electrolysis is carried out, and it separates the two gases, and you can test them. It's a short video, and you really should watch that. I don't have the liberty, I think, to show that in my video, but I'll include the link on Blackboard. You really must watch it. It's short, it's fun. Alright, so here's the setup we're going to do. This is what it'll look like in real life. Let me talk about it a little bit here. So we have a tank, a glass tank, and we have some distilled water, and we throw in some sodium sulfate to give it some ions so that it can carry charge. We put in some universal indicator that'll indicate pHs. Universal indicator, look at the colors at the bottom here. Universal indicator is a mixture of 3 different indicators, and it shows different colors for different pHs. It's not accurate, but it's a good approximation. At any pH below 4, it's red, so we can't distinguish below 4. At any pH above 10, it's purple, so we can't distinguish above pH 10. But between 4 and 10, we can estimate the pH of a solution pretty well, actually, based on its color. So in this setup, we have a DC power supply, and the negative terminal, that's the black lead here, is connected to the blue wire, and ultimately goes to the black wire through an ammeter. I'll show you in a minute on the other diagram, but black and blue go to this copper electrode. They're pushing electrons to it. Electrons will be pushed into solution and reduce the water. When water is reduced with negative charges, it forms hydroxide, which is negative, and hydrogen gas. And you'll see the hydrogen gas bubbles coming rapidly off the copper electrode. You'll also see, if you let it stand for a while, the solution will turn blue to purple in this vicinity because hydroxide ion has a color of blue to purple with the universal indicator. At the same time, from the positive terminal of the DC power supply, electrons are being pulled into it, and that red wire is connected to the carbon electrode, which will be the anode. When electrons are being taken away, a loss of electrons is oxidation, and so water will be oxidized at the surface of the carbon anode. When water is oxidized, when electrons are taken away from it, it produces H+. That kind of makes sense, right? Take away electrons and you get a positive charge, and oxygen is formed. And you will see bubbles of oxygen gas forming at the surface of the carbon anode, and over time you'll see the solution near the anode turn red because hydrogen ion is being released, and that lowers the pH. We'll measure the voltage by connecting a voltmeter in parallel with the power supply. We'll measure the actual current by connecting an ammeter in series with the power supply, and I'll show you the setup for this in the lab. And we'll carry out the electrolysis and make some observations and take a couple of simple readings. Let's go over what's actually happening in these reactions. So I may repeat myself, but that's okay. Here's the DC power supply connected in parallel to the voltmeter, connected in series to the ammeter. From the negative or black terminal of the power supply, electrons are pushed through the ammeter so we can measure the current. We're connecting it to our copper electrode. Since electrons are being forced here and forced into solution, water is going to be reduced here by the electrons, and wherever reduction occurs, that is called the cathode, and that is the definition of a cathode. The cathode is the electrode where reduction occurs. It occurs because electrons are being forced to it and into solution. So the surface of the cathode will become negatively charged. What color should that be? Maybe blue electrons. Okay, so these are electrons building up on the surface of the electrode and then going into solution, and we'll see that the reduction of water forms hydroxide ion, which turns the solution blue or purple here because it's basic, and also hydrogen gas bubbles will be formed rather rapidly on the surface of the cathode. At the same time, the positive terminal of the power supply is going to be taking electrodes from the opposite side, pulling it from the carbon electrode. So the surface of the carbon electrode will be positive. It's electron deficient. Electrons will be taken from the water molecule. When electrons are being taken, something's being oxidized. Oxidation is loss of electrons. So the definition of the anode is the electrode where oxidation occurs. That is always the case. So when water is losing electrons or being oxidized, you will see hydrogen ions being formed. Now how will you see that? Well, you see the solution will turn red because it's becoming acidic. And also we'll see, to a smaller extent, we'll see bubbles of oxygen gas formed at the surface of the carbon anode. I will explain the use of the multimeters in the lab and how we set them and what they mean. Let's go through the reactions that occur at the cathode and anode. So at the copper electrode connected to the negative terminal, that will then be the cathode. And it's cathode because reduction is occurring, and that's the definition of a cathode. It's the electrode where reduction occurs. Now it'll be negatively charged where we're, in the case of an electrolysis or electrolytic cell like this, where we're forcing electrons to the cathode will be negative. But be careful when you're talking about a battery in which the battery is supplying the charge, the cathode will actually be positive. So don't memorize the charge of the cathode or anode, but be sure to memorize that the cathode is where reduction occurs. You'll learn more about this later. Don't be distressed if you don't get it all, but this is a good starter for you. At the cathode, we have water that's being reduced, gaining electrons. And when it is reduced, it produces hydrogen gas and hydroxide ion. We need to balance this for charge and mass. You can see that the oxygen is balanced but not the hydrogen. Just as a general rule, anytime you see an even number of something on one side and an odd number, a good approach is to double up on the odd number like this to make it even, and you can usually find a common multiplier. So I have 4 hydrogens on the right, put a 2 here, and now I have 4 hydrogens on the left, 2 oxygens on both sides. So this is balanced in terms of mass, but not in terms of charge, and both have to be balanced. On the left-hand side, the charge is 0. On the right-hand side, it's -2. How do we balance charge? There's only one way you can balance charge, and you can only do it by adding negative charges, only by adding electrons. You can't add positive charges to balance any chemical reactions. So that's now balanced for charge and mass. Let's look at the other electrode, which is the carbon anode. And oxidation is occurring there because it's attached to the positive power supply, and that's pulling electrons away from it. So in a case of electrolysis or electrolytic reactions like this one, where electrons are being pulled from the anode will be positive. But in the case of a battery, the anode is negative. So don't memorize the charge, memorize the definition that oxidation always occurs at the anode. So here water is reacting again. This time it's producing oxygen, and the solution will turn pink, indicating that we have hydrogen ion also being produced. Now this is not balanced either. We have to balance this for charge and mass. So oxygens aren't balanced. Let's put a 2 here, and now we have 4 hydrogens, 4H+. So it's balanced now for mass, but not for charge. How do we balance this for charge? The only way to balance an equation for charge is by adding negative charges. We have to add electrons, not positive charges. We need to have 4 negative charges here. And now this is balanced. We're going to combine these two half fractions together because they have to occur together in stoichiometric ratio. So to do that, we have to have the same number of electrons gained and lost. In redox reactions, we count electrons. In acid-base reactions, we count moles of hydrogen hydroxide, right? But in redox reactions, it's electrons. So I need to multiply this first reaction by 2. So now I have 4H2O plus 4 electrons. So 4 electrons are being gained to offset the 4 electrons being lost in the second half reaction. That's 2H2 plus 4OH minus. Now I can add those two half reactions together and come up with the overall reaction. So on the left-hand side, I'll have 6H2O plus 4 electrons. On the right-hand side, we have oxygen plus 2 moles of hydrogen plus 4 electrons plus 4H plus 4 OH minus. Now the electrons will always balance in these combined half reactions because we planned it that way, so I don't normally carry them down. I just did it this time to show you. You can normally leave them out. It's interesting here because in the gap between the two electrodes, hydrogen ion meets hydroxide ion, and they will instantly combine to form water molecules. So actually what we produce in this reaction is 4H2O on the right-hand side. We can cancel like terms from both sides. If I subtract 4 water molecules from both sides, I'm left with 2H2O goes to O2 plus 2H2. So twice as many moles of hydrogen are produced as oxygen. And you'll see that when you do it. You'll see at the copper cathode, the rate of evolution of gas, the hydrogen gas, is twice as fast as the rate of evolution of oxygen gas at the carbon anode. One more thing we want to do here is consider the potentials, the voltages involved in these reactions. If you take a look at the next page in this lesson, and by the way, this is right out of the appendix, page 259, we have the half reaction reduction potentials for a group of metals and some others. And fortunately, this is not the first time you've seen this. If you did the lab regarding activity series of metals in 161B, you'll have seen this before, so it does need repetition. It's not the easiest thing. So here we have half reactions in which ions are being reduced. Lithium plus 1 is gaining electrons, being reduced. All of these species on the left are being reduced by gaining electrons. So therefore it's called a reduction potential. Potential is the voltage involved in the process, and that's in the right-hand column. If that's a negative value, that means it's unfavorable. You would have to apply, in this case, at least 3.05 volts to force lithium ion to accept an electron. Lithium ion is much more stable than lithium metal. On the other hand, if the potential is positive, as we see down near the bottom, then these are favorable reactions. Copper 2 ion would want to and would spontaneously gain electrons to form copper metal. We're going to look up the oxidation and reduction potentials for these half reactions. So here I have highlighted the reduction of water at the cathode, because that's where reduction occurs, to produce hydroxide ion and hydrogen. That's negative 0.83 volts. That means it's unfavorable. We'd have to apply at least 0.83 volts to force that reaction to occur. That's only half of the reaction. The other half is the oxidation of water to hydrogen, ion, and oxygen. If we go down further, we'll find that reaction here in blue as well, but you'll notice it's reversed. Here it's written as the reduction of oxygen and hydrogen ion to produce water. We have to reverse this. Recall that in every redox reaction, something's gaining electrons, something's losing them, something is being oxidized, something's being reduced. In the tables, they list them all in one direction. You'll always have to reverse one of these half reactions. In this case, we want to see the oxidation of water to hydrogen, ion, and oxygen, so we have to reverse this reaction. So instead of being positive 1.23, it's negative 1.23 for the oxidation of water. And so you'd have to apply at least 1.23 volts to force this reaction from right to left. Let's put those values into our reaction equations up here. At the cathode, the voltage required that had to be applied, the term for this is called E0. It means standard EMF, or standard voltage under standard conditions. Now it does vary slightly with temperature and with pressure and number of moles, but under standard conditions, which you'll learn about later, these are the values. And the other values will be fairly close to it. This is equal to minus 0.83 volts has to be applied to make this work. Now you wonder, what if I have to double the number of moles of each species? Does not affect the voltage. It only affects the current. You'd need twice as many electrons, but the voltage is the same regardless of the number of moles involved. For the oxidation of water, the standard electrode potential for that is negative 1.23 volts. If we add those together, we find for the entire reaction that would be negative E0 equals negative 2.06 volts, which tells us we have to apply at least 2.06 volts on our power supply to force it to occur. Now in reality, we usually have to apply a little over potential, something a little higher. There's always some loss of energy in any transfer process in reality, but it'll be slightly greater than 2.06 volts. So that, I think, is a pretty good start for your first lecture. Sorry to put so much at you at once, and this will be reviewed over time, but we needed to get started now for what we're doing in this first lab. In experiment number 1, which you'll be doing in the first week, you'll be doing carrying out some reactions involving hydrogen. Hydrogen anion, hydrogen cation, and such. Hydrogen molecules will generate some by electrolysis. So you have some theory to read. Notice here that's about 4 or 5 pages long. It says 12, but a lot of this is just stuff. So there's about 4 or 5 pages of theory to read. I'm just kind of flipping through it. The element hydrides, fuel cells of some interest, the pH scale, which I suspect you're pretty familiar with, and some information regarding interconverting pH and pOH, H plus and OH minus concentrations, which I think you've already covered in another course. Here's the information about electrolysis that I just explained to you. These are the actual experiments we're going to do. As well as electrolysis, we'll have some other short experiments involving hydrogen, some instructions on how to calibrate a pH meter. I will show you that in week 1. And then materials from the stockroom, that's for the stockroom person to use. So it isn't as bad as it might look, but there's probably about 4 pages of solid theory for you to read. So after you've completed the experiment, on the last 2 pages we have the lab report. And again, this is a fill in the blank. It must be handwritten. I will not accept it if it's typed. You can probably guess why. And if you have read the theory and done the lab, this should probably only take maybe 10-15 minutes to do. I'm not kidding. Yeah. So, and just hand that in handwritten in week 2, in the second week. The lab reports will be short if you spend the time reading the theory. That's it for this first lecture. Thanks for listening.